Swayam Prabha. Digital India. Educated India.
Hello and welcome to this manufacturing process technology part 1 module 44. We were talking about the various different kind of chips that were produced, like the continuous, discontinuous, one with built up edge, so on and so forth in case of machining. So let us actually now look at a little sort of different aspect here. I think we had discussed about the built up edge in great details and said that there is going to be residue formation on the surface on one hand, which will result in sort of a bad surface finish for the material on one hand, and on the other hand, as you can probably see that because of the built up edge formulation on the top of the, so because of the built up edge formulation on the top of the tool, it acts like a virtual material of higher hardness and starts grazing the workpiece, thus protecting the tool life. Okay. So, it is a trade off really between the surface finish and the increased tool life that you are sort of involved in when you try to deposit or when you try to analyze the situation where machining happens with built up edge. So, built up edge can obviously be reduced because most of the time the requirement is that of a higher surface finish. So, you can decrease the built up edge by increasing the cutting speed, for example, decreasing the depth of cut, increasing the rake angle. So if you are having some kind of a grazing rake angle, this right here is the rake angle. So if alpha is more and this tool is somewhere which is like sort of grazing the surface, you can see that probably you can increase the rate at which chip formulation is happening at lower temperatures or lower using lower powers. You can use a sharper tool again to remove the built up edge completely. You can use an effective cutting fluid so that there is sufficient amount of heat transfer and the chip does not really weld whatever is formulated here, although it is highly strain hardened, it does not weld anymore to the tool surface, so that the BU condition may come. So using tool with lower chemical affinity for the workpiece material is another important way out for sort of preventing the built up edge from happening. So if I looked at the hardnesses, and these are all the HK values of the chip as well as the built up edge and the workpiece. So you can see this built up edge to be formulated as a part of the tool maybe, so this is the tool actually, and you can see the hardnesses of this region, the built up edge region is really very high, even higher than the hardness of the work material, and obviously that is the reason why it grazes onto the work material. So hardness is as high as 704, for example, okay, 704 HK Knoop hardness is recorded here in case of this built up edge, whereas if you look at the standalone chip again, the chip does not have hardness more than about half the value, about 372, and so is true for the workpiece surface. So no reason because of all this, the built up edge is kind of plowing on the surface and is able to successfully cut metal as a virtual tool surface. So the figures here show some high resolution pictures of what happens when the turning or milling processes happen and what happens because of the built up edge in turning and milling operations. We also need to explore the temperature rises due to heat lost in cutting, and I think I had theoretically modeled this earlier and also helped you to solve numerically the temperature rise in the cutting zone. Now the major adverse effects which happens because of a temperature rise is that it lowers the strength, the hardness, the stiffness, the wear resistance of the cutting tool itself. Okay, so the tool life is the most which is affected, and in fact we are going to do some formulations to sort of optimize the cutting conditions so that the tool life can again be enhanced, and you do not need tool changing anymore, or minimum times tool changing requirements are there, so that you can actually do machining at a lower cost. So another important bad effect that temperature rise would have is that it causes uneven dimensional changes, particularly in the machining parts. Think of it, all the metals are amenable to change dimensionally when subjected to higher temperatures. They all have coefficient of thermal expansion, and so therefore, there can be overall change in the dimensions while the cutting process is on, which can be again affecting the assemblies into which these parts would be going after the machining operations are performed. So, they can induce thermal damage and metallurgical changes in the machined surface. Properties get adversely affected because of that. And sources of heat in machining, if we look at, are really the primary shear zone, the tool chip interface, and the sort of a tool rubbing on the machined surface using particularly tools which are worn out or not having high sharpness, etc. So, this is a sort of a recall of what we had also seen earlier in terms of a model, that what impact the temperature rise would have onto the machined surface in question. So, if I look at the various temperature distributions which have been found out in the primary zone, the tool chip interface, you can see that there are very large temperature gradients, particularly in the cutting zone. If you look at the gradient here, for example, the temperature line, the isotherm here, which is recording 130 degrees Celsius, is just closely spaced to the tool temperature, which is about 500 degrees Celsius. And if you look at the same here, you can see the tool where the maximum chip pressure happens, and you already have seen it theoretically how, because of this chip pressure, there is a variation in the temperature. So, the maximum temperature rise is more or less similar to 700 degrees, okay, and this probably leads to some kind of a plastic welding between portion of the chip onto the tool surface. Okay. So, the distribution happens in a way that there are very large temperature gradients in the cutting zone, 500 to 113 in 130 in a matter of just a few microns, and because of that, again these points here have the tendency to formulate what you call the built-up edge again. So, the measurements of such temperatures or temperature distributions can be experimentally made by using thermocouples, which can be either placed on the tool or the workpiece surface, or in a non-contact manner through infrared radiation. So, you can use a radiation pyrometer, for example, from the cutting zone, which only measures the surface temperature. You cannot go into measuring the depth temperature. Obviously, thermocouples can be placed in a manner at a certain depth within the tool, where you can actually get this complete isotherm. You can see here, for example, you have temperatures even within the tool, like in this particular portion or in this particular portion. So, that can only happen when you have an embedded architecture for doing measurements, and there are experiments where embedded thermocouples are put into the tools for carrying out experimental determination of the temperature isotherms. The other issue which I wanted to really emphasize is that because of all this temperature rise and severe plastic deformation of the chip material, formulation of built-up edge, there is an effect on the tool life, particularly because of the wear and failure in many cases of the tool, or in some cases sort of a protectant layer which happens because of which the tool life may increase. Okay. So, tool wear is gradually is like a gradual process which is created due to high localized stresses at the tip of the tool, also because of high temperatures, especially along the rake face, sliding of the chip along the rake face, sliding of the tool along the newly cut workpiece surface, and this normally happens in case of tools which have particularly worn out, the sharpness level has decreased, and this is called the flank face wear, which one has to avoid because it results in a bad surface finish, and that should be avoided generally in the machining process. So, the rate of tool wear depends on tool and workpiece materials, depends on the tool geometry that you are using, what is the kind of the tool geometry, which typically includes all the tool angles or even certain things related to the change in shape because of flank wear, etc. The tool wear and tool life also depends on process parameters, particularly cutting conditions that are very significant to the change in the wear rate or the tool life, and then finally on cutting fluids, because these are used to normally do the heat transfer in the cutting zone, so that the overall temperature does not go to a value where the built up edge formation etc., starts to take place. Okay. So, these are some of the dependent parameters which govern how what kind of tool life can be there or what kind of wear characteristics of the tool would occur. So, there is an empirical relationship given by Taylor which basically tells about the relationship between the tool life and the cutting speed in meters per minute, and this is also better known as Taylor's tool life equation. So, the tool life T in minutes taken to develop a certain flank wear, where flank wear is really the wear which occurs on the relief face of the tool or the flank face of the tool due to rubbing of the tool on the machined surface, and typically this wear is also the adhesive or abrasive wear, and also because of high temperatures adversely affecting tool material properties. So, as per the Taylor's tool life equation, V t to the power of n is equal to a constant c. It depends on really the cutting conditions, and if you look at some of the ranges of this exponent n in case of Taylor's equation for the various tool materials. So, for high speed tools, steel tools for example, the n varies between 0.08 to 0.2. For cast alloys it varies between 0.1 to 0.15. Carbides it varies between 0.2 to 0.5. Coated carbides 0.4 to 0.6. Ceramics 0.5 to 0.7. So, obviously as the n is more and more, you can see that the tool material is getting harder and harder. Okay. And the only difference is in case of cast alloys versus high speed steel, which comes here. So, note that in this Taylor's tool life equation, the exponent n and the coefficient c are basically determined experimentally, and you can say that c is really the cutting speed corresponding to a tool life of 1 minute. So, if t were equal to 1 minute, then c equal to v. So, that is how we define the tool life constant in case of the Taylor equation. To appreciate the importance of the exponent n, if I can just simply rearrange the Taylor's equation, it results in t equal to c by v to the power of 1 by n. So, thus for a case where c is constant, let us say for a certain set of tool or certain cutting conditions, certain set of cutting conditions including the tool and the material, if I have a smaller n, which means higher this coefficient 1 by n. So, you should have a smaller tool life. So, that is more so because if I just looked at this part of the equation here, obviously as we have already told that the c is constant. So, this equation can be written down as c to the power of 1 by n divided by v to the power of 1 by n, and the c to the power of 1 by n is any event a constant k divided by v to the power 1 by n. So, if n is a smaller and 1 by n is bigger, so obviously the tool life is going to go down. Okay. So, which makes sense, which is being represented in this particular equation. So, tool life equation can accordingly be monitored for different processes. For example, for a turning operation, the equation may be modified slightly to a form v t to the power of n d to the power x f to the power of y equal to c. D obviously is the depth of cut. So, it is same as the initial cut thickness, or you can say this is T1 or T0 as we had earlier taken in merchant circle, and f is the feed of tool in millimeters per revolution. Okay. And again the coefficients x and y are determined experimentally for each cutting condition, and it is more like an empirical relationship, just like the original Taylor's tool life equation of v to the power v t to the power of n equal to c. Extending this logic further, the tool life curves can be plotted for different values of n. The exponent n can be determined from the tool life curves really. You can see here, you already know that v C by V or some constant k, which is c to the power 1 by n by v to the power 1 by n equals the tool life t. Obviously, if n is a smaller value and 1 by n is quite large, then if v varies, let us say v increases or v just varies. So, for a larger coefficient here, the tool life should be able to vary more. So, if supposing v increases in this particular condition and n is really small or 1 by n is really big, then the tool life should decrease much faster in comparison to the condition where n was bigger and 1 by n was relatively smaller. So, therefore, you can have a higher slope situation here, that for a little variation in the cutting speed you have a higher variation in the tool life just because of the decreasing value of n or increasing value of 1 by n. So, therefore, this line for example corresponds to high speed steel, which probably has a range of 0.08 to 0.2 n value. This is cast alloys, cast cobalt alloys. This is for example carbide, this for example ceramic, where I think I had earlier mentioned just about 1 or 2 slides back that for example in the carbide scales it is 0.2 to 0.5, that is the value of n. So, n has increased here really. Coated carbides and ceramics, they are even higher, 0.4 to 0.6, 0.5 to 0.7, and so therefore, this falls in line with the logic here that the ceramic tool just because the n value is higher there should have a lower variation in tool life in comparison to a increase in cutting speed as compared to let us say carbide, cast cobalt alloy and high speed steel. So, once again just trying to reiterate here that as the n decreases and 1 by n increases, a smaller amount of variation in V would result in a larger amount of variation in T, which actually is determinant of this tool life. So, n can also be negative at a low cutting speed, a situation where an increase in speed would also result if supposing n is very small and 1 by n is actually large. So, an increase in speed would result in increasing the tool life. Temperature also influences wear, as the temperature increases the flank wear rapidly increases. So far we have kind of seen what are the various possibilities and how you can obtain the n values from plotting the tool life with respect to the cutting speed and determining it from the Taylor's equation Vt to the power of n of c. This equation is particularly significant when we talk about machining conditions and optimum machining conditions, particularly used to find out what is the overall cost of the machining process or overall time in the machining process. And this particularly holds true for NC CNC systems, where there are many such inserts and there is a tendency of the inserts to be repeatedly weared out because of high speed machining processes, and you have to actually either grind them or increase the sharpness of these tools before reuse. So, there the optimization or the criteria which are followed for the optimization are totally dependent on the tool life equation. And we would like to present one such case here, where we want to determine the machining conditions and manufacturing times, having specified the workpiece material, machine tool and cutting tool. The question is what can be controlled to reduce the cost and increase the production rate, and the controllable variables in this case are cutting speed, for example V, the feed F, the depth of cut D, jointly the velocity, cutting velocity, the cutting feed and depth, they are referred to as machining conditions. And so, there are a number of models which specify the optimal machining conditions, out of which the two that I am going to teach here is one is the minimum cost model. So, this is actually the minimum cost model, and the other is actually the again minimum time model, which is related to the total manufacturing time. So, let us suppose that in a particular case of machining you have a cost rate which includes labor and overhead cost rates. It could be some unit of currency per unit time. So, you also have a tool cost per cutting edge, which depends on the type of tool that you use. It may be an expensive tool which has slightly higher tool life. Okay. So, C1 may be higher in that particular case. C is obviously a constant in the tool life's equation V t to the power of n equal to C. V is the cutting speed in meters per minute. Let us assume F to be the feed rate millimeters per revolution, D to be the depth of cut in millimeters, and we are just trying to evaluate probably a CNC turning process in this particular case. N happens to be the exponent in the tool life equation, and T1 is the non productive time consisting of the loading and unloading time for the part in the machine as reported in minutes, and Tc is the machining time per piece in minutes per piece. The actual cutting time per piece may be slightly different than the machining time per piece, because this, if you are talking about a CNC system, involves the absolute positioning in the point of machining and some displacement of the tool all the way to the start of the work, and therefore the TAC, actual cutting time per piece, may be slightly different than the TC, but in all the cases that we would be considering here, we will probably consider them to be similar. They are not very much different, because obviously all the controllers are designed to have almost optimum or minimum possible idle time, and that is how the path planning in the motion controllers are done. T is the tool life in minutes, and Td is the time to change a cutting edge. Cutting edge means an insert. Therefore, if you are wanting to change an insert because of its wear, you need about Td time to change that insert in the machine. So, having said that, let us actually bring out what is the kind of cost of labor, overhead, tooling, so on and so forth, which is used in sort of machining, and then try to optimize or minimize the cost in this particular case. So, the minimum cost per piece in this case consists of the following costs. So, the average, let us say the average cost per piece to produce a workpiece consists of non productive cost per piece plus machining time cost per piece plus tool changing cost per piece plus the tooling cost per piece given the Taylor's tool life equation, which is V t to the power of n equal to C, a constant. So, obviously, the Cu, which is also the cost per component that you are manufacturing on this high throughput system, comprises of this non productive cost, which is actually very well written as the non productive time, which is involved in loading, unloading of the sample onto the machine, times of the total amount of cost rate of the labor, overhead, etc., which happens to be multiplied with time T1 to give the overall cost. So, this is C0 T1. The cost per component also includes the machining time cost per piece. So, the total amount of machining time in this particular case is taken as Tc, okay. And during this time, the total amount of overhead cost that is spent is basically again C0 per unit time. So, I can say C0 Tc as the total amount of machining time cost per piece plus the tool changing cost per piece, and here we have to bring in the tool life, because we know that T is the tool life and the actual cutting time TAC in this case supposing involves more than one tools. So, really the TAC by T would be the frequency of change of the tool, and so that many number of times, that means TAC by T times, you have to spend the time to change cutting tool in each case, and the total such time spent would be equal to Td times of TAC by T, where Td is the frequency, Td is the time per cycle of change, and TAC by T is the cycle frequency of the change per se, and during that time you are again spending the labor and overhead costs. So, I just multiply this with C0. So, this gives you an idea of what kind of time, because every time there is a change and there are n such changes, because you have to extinguish n tools in order to consume this whole one pieces cutting time, which is TAC. So, n times of Td really is the total time, and C0 n times of Td is really the total cost which is involved. So, this is the total changing cost per piece, and then we have a tooling cost per piece, which is actually equal to again the tool cost per cutting edge, and you are actually including around n cutting edges for the cutting process given by TAC by T, the frequency, and this times of C1 basically gives you the total amount of tooling cost per piece. And so, this summation here of all these terms together give you what you call the cost per component. Now, let us actually try to see whether what is the optimum solution, so that the tool life probably can change accordingly and the overall cost can come down for certain conditions of machining. And so, the first thing that I would like to illustrate here, that if we consider a single pass turning operation, and supposing we also further consider that L, capital D and F are the length of cut in mm, diameter of the workpiece, again in mm, and feed rate in mm per revolution respectively. Then the cutting time per piece for a single pass operation can really be given as Tc, which we will approximately consider to be TAC in this case, considering the controller to be optimized for the home position setting, etc., for the tool. And so, that becomes equal to pi L D, where remember the D actually and the length of cut both are in millimeters, divided by 1000 Vf, where V is the velocity again, and this velocity, as had been recorded earlier, is given in meters per minute. So, we can always have this equal to 1000 millimeter per minute, and F is basically the feed rate, which is millimeters per revolution. So, obviously, the pi L D gives you an idea of the total surface area which is removed, and that times of that divided by 1000 Vf gives you an idea of how much time in a single pass would be taken to remove off this much amount of. So, the TC here actually is represented as the more or less the TAC. So, the cutting time and the actual cutting time are similar to each other, and they are given by this equation pi L d by 1000 Vf. L and d are both in millimeters, velocity being in meters per minute has to be converted into 1000 millimeters per minute, and F again is the feed rate in millimeters per revolution. Okay. So, this really shows you the cutting time in a simple single pass turning operation, and upon substituting these values as well as tool life equation in the cost per piece equation as obtained in the last slide, we get already the Cu was defined as C0 T1 plus C0 Tc plus C0 Td times of Tac by T plus C1 Tac by T. Obviously, we know what is the actual cutting time or Tc value here from geometrical parameters, length of workpiece, diameter of the workpiece, the feed rate and the velocity of the cut and or cutting speed, and also we know from the tool life equation that T can be written down as C by V to the power of 1 by n, meaning thereby 1 by T can be recorded as V by C to the power of 1 by n. So, having said all this, we substitute these values back into the cost equation. So, we have C0 times T1 plus C0 Tc, which is again pi L d by 1000 Vf plus C0 Td, the time to change a cutting edge in minutes, times of Tac again, which is pi L d by 1000 Vf times of 1 by T, which is V by C to the power of 1 by n, plus C1 times of again Tac, which is pi L d by 1000 Vf times of V by C to the power of 1 by n, so on and so forth. So, that is what you know about cost per piece, and having again said this, and there is of course a Td term here, which means the time to change the cutting edge. So, now the feed rate and depth of cut for any turning operation, single pass turning operation, are normally fixed. So, the feed rate and which is defined by F in this particular case, and the depth of cut and also the initial dia of the workpiece are normally fixed to their allowable values, whatever they may be, and therefore, the cutting speed really is the decision variable upon partially differentiating Cu with respect to V equating to 0 and solving, we obtain the minimum unit cost cutting speed. V min. So, let us now do this by substituting dcu by dv equal to 0 and try to see what is the implication of that, what is the final form of the equation which would emerge actually based on that. So, the dcu by dv in this particular case can be written down as C 0 pi L d divided by 1000 f times of minus 1 by v square plus C 0 pi L d T d divided by 1000 f c to the power of 1 by n d by dv to the power of v to the power of 1 by n minus 1 plus C 1 pi L d by 1000 feed f c to the power of 1 by n times of T d times of d by dv of v to the power of 1 by n minus 1, and that becomes equal to 0. So, C 0 pi L d divided by 1000 f times of 1 by v square equals to pi L d by 1000 f c to the power of 1 by n times of C 0 T d plus C 1 times of 1 by n minus 1 v to the power of 1 by n minus 2, and therefore, we can obtain a condition from this equation that v to the power 1 by n becomes equal to C 0 divided by 1 by n minus 1 times of C 0 T d plus C 1 times c to the power of 1 by n. In other words, V minimum, which is corresponding to this value of V, becomes equal to the constant c divided by 1 by n minus 1 times of C 0 T d plus C 1 by C 0 to the power of n upon substituting the value of cutting speed in the tool life equation we obtain the optimum tool life. I can say this is T minimum corresponding to the minimum unit cost model as T min is 1 by n minus 1 times of C 0 T d plus C 1 divided by C 0. Okay. So, that is how you obtain the time minimum and the velocity minimum, where the term min corresponds to the velocity corresponding to the minimum cost of machining. So, this is how actually you try to optimize, and I am going to show with problem examples how V can be determined using the Taylor's tool life equation to do this optimization. So, we will subsequently talk in the next module about another way of determining the cutting conditions based on minimum time of manufacturing. So, then you can actually consider in various cases the optimum cost and the optimum time models to report the various cutting parameters. So, with this I will like to end this particular module, and I will look forward to again provide some optimization related issues in the next module, followed by the start of welding or joining processes module. Thank you so much.